record, and hide the panel. All right. So last time we stopped where we were talking about these methods of proof, right? So these are ways that we can reason logically, tell a story to prove something, to say, this is true. And so we go from a hypothesis or a conjecture of, I think this is true. And so actually conjecture comes first. Conjecture. And then we've got a hypothesis of this is where I am starting. I am assuming that this is true. And then we reason logically to get to our conclusion. And the method of reasoning is the type of proof that we do. So we've got either a direct proof or an indirect proof. We talked about direct, which is we assume that if we're trying to prove P implies Q, we assume P is true. We reason our way to Q being true. And we saw an example for that down here, where we said, prove that the sum of an even integer and an odd integer is odd. And so there's a little bit of work there getting it to be in the form of P implies Q, where we have to break down the natural language of it into actual math. And then we can write with words. And so we can say, let X be an even integer, Y is an odd integer. That's our hypothesis, that's our assumption. And we know that even the form of an even number looks like X equals 2K, where K is an integer. We know that an odd number looks like Y equals 2J plus 1, where J is an integer. And so these two sentences are stating, like, this is what we know. And then we say, okay, so we've got an odd integer and an even integer. Let's add them together. And so we have X plus Y is equal to 2K plus 2J plus 1. So we're just adding the form of an even number and the form of an odd number together. And then we can factor a 2 out from there. And then we know that the integers are closed under addition. So that's got to be an integer. And then this looks like an odd number. And so once we get that, that's like, we were trying to prove that it is odd. So that's our conclusion, to say we've reached the form of an odd number, therefore we're done. Oh, the question. Yeah. All right, so that's the direct proof. And then we have the contradiction style proof, where I don't think we actually got to the end of it. Let's hold on. Let me go back up here. So for contradiction, if we're trying to prove P implies Q, then we prove this indirectly. So we assume two things. We assume that P is true and not Q is true. So we're assuming that our hypothesis is true, but the conclusion is false. So basically saying, like, this can't happen. You'll see a lot in contradiction proofs of suppose not. So like, you've made this statement and I'm going to suppose that it's not true, and then reason my way to what we call a contradiction, which says that I supposed something in the beginning, that must have been false. And so, yeah, so we do that. We work our way to a contradiction, which is when one of our assumptions ends up not being true. And then we can say for our conclusion that P implies Q is true. So we have our example down here of prove that if the sum of a real number and itself equals itself, then the number must be 0. So if the sum of a real number and itself, so we're doing x plus x, and we get x in return, we want to prove that x has got to be 0. So let's take a second to we'll talk about this with counterexamples. When you're given a statement like this, like on an exam, you might be asked like prove or disprove, where I'm not telling you that it's true necessarily, but you have to kind of think about it first. So like thinking about this, is it possible that there's another number for which x plus x could be x? So we can try like small numbers, like, so 1 is a real number. 1 plus 1 is 2, which isn't 1. -1 plus -1 is -2, so not -1. Let's see. 1, -1. It says real numbers, so we could have, like, if we chose a rational number, like 1/2. 1/2 plus 1/2 is 1. An irrational number plus an irrational number. Let's see. Square root of 2 is irrational, but adding it twice just gives you 2 times the square root of 2. So this is like, we first we got to think of, is this actually true, to kind of convince ourselves to prepare us to prove it. So once we've done that and we're like pretty sure that we agree with the conjecture, then we start to look at proving it. So we break it into its statements. So we've got A of x and B of x, and we want to assume A of x is true and not B of x is true. And so that's how we write it in symbols. So let's write the proof in words. So we'll start off by saying what x is. So we'll say, let x be any real number. And then we want to say our hypothesis, where suppose x plus x equals x, but x does not equal 0. That's our hypothesis. So we're all set up to do some contradiction. So now we get to do some algebra. And so, I don't know. So this is our equation that we've got. And so we've got an x and an x here. So then we can say 2x is equal to x. And in this case, we're assuming an equation, right? We're assuming x plus x equals x. So we've got both sides of the equal sign to work with here. So we've got an x on both sides. And so I could say, so there's a couple of different ways I can say this. Again, proofwriting is a little bit of an art. And so I could say, like, that implies that 2 equals 1, like we divide on x by both sides. But that may seem like a little bit of a gap. So let me add some words around there. So dividing by x on both sides gives us 2 equals 1, which is a contradiction, right? The point of contradiction is to assume that the thing we're trying to prove is false, and then reach a point where something so crazy and so like obviously false has happened that our assumption must be false. So therefore, x must equal 0. You could also have said, therefore, x equals 0. So like spelling it in symbols instead. The other way the book says is instead of getting 2x equals x, you could have said like subtracting x from both sides. We have x plus x equals x, or no, no, that's okay. And then we get minus x, so x equals 0. And that's another way to reach that contradiction, where we have assumed that x is not equal to 0, but then we said, oops, x is 0. Guess we were wrong. And so then we say, that's a contradiction. We're done. Questions? All right, I want to tell you about a super famous proof by contradiction. There's actually 2 of them. We'll probably look at the other one on Monday. These are the proofs that when I took what was Math 103, I don't know what it is now. It's like the intro to proofs. As a math major, I took this class from Jim Sauerberg, and he taught us these proofs, and he said, if I run into you on the street 20 years from now, I want you to be able to prove these. These are also proofs that some mathematicians have said of like, they're the most beautiful proofs in the world. One guy said like, God has a book of proofs, and these 2 are like in that book of like, they're the most beautiful and concise, and they're proofs by contradiction. And so we want to prove that prove that the square root of 2 is irrational. And so first, what's a rational number? Any number with a decimal. Kind of. So we've got real numbers, so those are decimals, and whole numbers, like 1's a real number. 3/4 is a real number, 0.75. A rational number is, yeah.
No real numbers, one over the other.
Yeah, so 2 integers. So we can express it as a fraction, where a and b are integers. Irrational numbers, I don't know if there is probably a Blackboard letter for irrational numbers, but I don't remember that off the top of my head. But the things that we'll need to know for this, so we've got real numbers, which include rational and irrational numbers. Then rational numbers are, we write a over b, where those are both integers. So that's what we need to know going into this. So we're going to prove by contradiction. So I'm going to set up like, I'm going to prove this by contradiction by suppose that it's not. So we're going to assume that we're working with the square root of 2, and we're assuming that it's not irrational. And so not irrational, what's the word for, there's 2 nots there, and so they cancel out. And so therefore we say that square root of 2 must be rational. and we can write it in the form of a rational number. So we can write it square root of 2 equals a over b. And so something to think of when we're looking at rational numbers is, let's consider 4 over 2 and 6 over 3 and like 10 over 5. So 4 over 2 is 2. 6 over 3 is also 2. 10 over 5. Why is my brain blanking? Is that also 2? That should also be 2. Right. So we can write a rational number in different ways. And so we want to just say, like, this is the most reduced it could be. And so the way that we write that is where A and B are not both even. So basically saying that, like, if we've got 4 over 2, we could reduce it further. We could go from 4 over 2 to 2 over 1, right? So it's not both even. So we can't, it's fully reduced. Okay. So that's just what it means to be a rational number. And so we've got this equation. Let's try some math in it. Let's get the square root out of there. And so I could just write 2 equals a squared over b squared, but I want to, that seems a little bit jarring. So I'll put some words in there and say squaring both sides, and then I can have my math where we've squared both sides. So we've got 2 on one side and then a squared over b squared on the other. And then we can multiply both sides by b since we've got an equation to work with. And so we can have 2 times b squared is equal to a squared. And a squared is 2 times something. So that tells us that a squared is even. So a squared is even. That's nice. Out of curiosity, if a squared is even, what does that tell us about a? So let's see. So if a squared is 2k, well, we could like square root both sides and that doesn't help us. But let's think of like 2 squared is 4, 3 squared is 9. 1 squared is 1. 5 squared is 25. So I think that we should be able to say that a is even. So let's prove that maybe really quickly. So if we've got a number a that's let's use a number m. If a is 2m, a squared is 4m squared, which is 2 times 2m squared. So if a is even, then a squared is even. If a is odd, a squared is equal to 2, 1 plus 1 squared, which is 4n squared plus 4n plus 1, which is 2 times 2n squared plus 2n plus 1. And so if we're able to show, like, as a side note, that if A is even, then its square is even. If A is odd, then its square is odd. Then by using that result, then we can say that A is even. So this is a corollary. So and so, okay, so you may be thinking, because I'm thinking right now, is so it's all well and fine to go from A being even to A squared is even. But the question is whether we can we go the other way? So that's the inverse of if we have an even square, is the original number square? Talk with your neighbor for a second. Are we allowed to go the other way?
At least one more time. What we're trying to.
Yeah, so we can say that if A is even, then A squared is even. But up here, we're trying to go from A being even to A, or we're going from A squared being even to A is even. We're trying to find the, I always mix that up. I think it's the inverse. Let me double check that.
Square is equal to A. I'm not gonna prove C.
And that's fair.
This gets me. I think it's the goals you used in it. Let me see.
Okay, what do we think? Can we do this or can we not do this? Okay, so the answer is that we can do it. Even though, like, in general, I would not recommend this method of proof. However, we're working with numbers here, with integers specifically. And numbers are either even or they're odd, right? Including 0. Like, all numbers are either even or odd. So if a number is a square, it's going to be either even or it's going to be odd. We've only got 2 options. And so if we show that a number is even, then its square is even. If a number is odd, then its square is odd. And so since we're only working with even and odds, then that's kind of why we're allowed to do this. So there's only 2 options here. All right, so that's why we're allowed to do this. So A squared is even and A is even. So back over here. we can write this like, if we write it as 2k, then we have 2b squared is equal to 2k squared, like substituting a. So that's fine. Let's square that and see where we get. And 2b squared is equal to 4k squared. I can, so this is a step where I might do multiple steps of math in one. So if we divide both sides by 2, we get b squared is equal to 2 times k squared. Can you see where I'm going? Maybe? All right, we're going to skip down below. Yeah, you're seeing where I'm going. So we substituted a, and then we get to a place where b squared is equal to 2k squared. So b squared, I'll just rewrite it, 2k squared. And so this tells us that b is even, which is okay, or b squared is even. And then we know by our corollary that b is even. Have we reached a problem? Yeah. So the method of proof by contradiction is you kind of just have to like keep going, keep going, keep going. And in each step, ask yourself, have I gotten there yet? Like you're like the antsy kid on a road trip of, are we there yet? Are we there yet? And in this case, we said B is even. Fine, so what? But if we look back, we said that A and B are not both even. And we've reached a point where they are both even. That's a clear contradiction. And so since that's the case, that means that square root of 2 cannot be a rational number. And so therefore, the square root of 2 is irrational. All right, so that's the proof. If I see you on the street in 20 years, I want you to be able to prove this. All right, any questions? Okay, so that's proof by contradiction. Let's go back up to the other type of indirect proof is contrapositive. And we proved by a truth table that the contrapositive and the implication are logically equivalent. And so the goal here is we assume the opposite of the conclusion. We work our way to the opposite of the hypothesis. And so our example for this one is prove that if the sum two integers is even, then either both integers are even or both are odd. Okay. So let's try and write it in symbols first. So turn to your neighbor and try and figure out if we're trying to prove P implies Q, what's P and what's Q?
Basically. Yeah, that makes sense. If you do this if the sum of two integers is equal, then it's P or slightly different P. Maybe mean a third letter.
Yeah, okay, so what do you think for P? Any ideas? Yeah, so maybe we call them X and Y. So equals 2Ks, so where K is an integer. And then we've got two outcomes, right? So there's also a method of proof that kind of it kind of ties into all of them. There's like proof by cases, where if you want to prove something and there's multiple cases that you have to consider, then you prove one first, then you prove the other. And so maybe Q1 is X plus Y, or let's see. So case one is they're both even. And so maybe X is equal to 2A and Y is equal to 2B. Is a way to say that they're both even. Or you could just say X and Y are even. And then our second case is both are odd. So X is equal to 2A plus 1, Y is equal to 2B plus 1, or X and Y both odd. And so when this is the case, then we'll take it one case at a time. So to prove this by the contrapositive, we assume that the conclusion is false. So let's choose the case, let's choose case one of both are even. So we're going to suppose X and Y are both even. And so X is equal to 2A, Y is equal to 2A. And we can't say anything about what adding them together is automatically, but we can add them together. And so we can say adding together. Again, just here's two words that help us connect the flow of our proof. So adding together X plus Y is 2A plus, that should be 2B. And from here, we can factor out a 2, A plus B. Wait, no. I've made a mistake. What's the mistake that I made? Well, did I make a mistake? Nope, I messed it up. So I kind of made a mistake, but I also kind of didn't make a mistake because, like if I'm trying to prove case one, then I did make a mistake where I assumed Q and then I'm proving P. So in the sense that if I'm trying to prove Q1, then I have failed. But if I try to prove Q1 and I assume the opposite, remember, even and odd is it's just a parity. It's a bit flip. Like either it's even or it's odd. And so if let's say I was actually trying to prove case two, then this is correct. And so X and Y are both even. And then I have gotten to a point where the sum is even. And so since I assumed, like, if I assume that they're not of that they're both odd, then they have to both be even. And this is the same for the other one. Another way to prove it, which the book does, is they go through this sequence of De Morgan's laws of saying that like the sum can't be even. And so let's write what the book has, and maybe that will also help you understand. So they say let X be odd and Y be even. So the other option for they're both odd or they're both even is that they're not. So they're not both odd. They're not both even. So one of them's odd, one of them's even. This is another way to get around the I've got two cases. And so one of them's odd, one of them is even. And so X plus Y is equal to, let's say X is odd, so 2A plus 1 plus 2B. And then this is going to be 2 of A plus B plus 1. And so then once we get here, then X is odd, Y is even, and we've gotten to the form of an odd number. And that's the opposite of what we assumed, right? We assumed this sum would be even. So we've proved the contrapositive. Okay. Let's also talk about all right, so there's also a section in the book of constructive proofs, counterexamples, and vacuous proofs. The constructive proof is one, so for example, I'll say prove there exists an integer n such that we've got this equation n squared plus n over 3n plus 8 is equal to 1. So we want to prove that there's an integer. And the way to prove this constructively is to solve the algebra. So take a second and work through this and then tell me what is n. Right. You get it? Some people still ready. I'll give you a second. Then we can factor it, n minus 4 times n plus 2. And so from there, we get either n equals -4 or n equals 2. And so once we've got either of these, nope, I messed that up.
You get that 3n plus 8.
Did I move 3n plus 8 to the other side? Yes. I multiplied both sides by 3n plus 8. Okay, so once I've got those two options, then my proof for this statement that there is an integer such that this equation equals 1, my proof is just plug it in. This is an example where I've basically been asked for an example of give me a number that satisfies this. And so let's say let n equals 4, and then you can plug it in to say 4 squared plus 4 over 3 times 4 plus 8. 16 plus 4 is 20. 12 plus 8 is also 20, which equals 1. So that's an example of a constructive proof. All right, and this one another one I want you to talk with your neighbor. If n squared is divisible by 9, then n is divisible by 9. Turn to your neighbor, talk about how you try to prove that. You don't need to write a proof, just talk about it.
Five. So it's just nine by nine, so not three to. Square the building and that's like nine times. Nine squared, yeah, nine squared, 6 4 9. Man, it's good one. How are you doing? Oh, sorry, I did it wrong, but I started with the second class. Yeah.
All right. Now, how do you prove this? Can you prove this? Yeah.
But squared is, 3 squared is 9, which is divisible by 9, but 3 is not divisible by 9.
So 9 divides n squared, but 9 does not divide n. What does that tell you? The statement is false. So we have found a counter example, which is typically like on an exam or on the homework, I will ask you to prove or disprove. And if we do that, then your first step should be thinking, can you find a counterexample? And so when you go to find a counterexample, start by thinking small. So think like, okay, 1 squared is not divisible by 9. Start with like 1, -1, or 0, and work your way up. And so here we know that I know an n squared that is divisible by 9. It's just going to be 9 as n squared. And so, yeah, so we get there. So like if we had started with n equals 9, then 9 squared is 81, which is divisible by 9. So that's not a counterexample. But if we reach a point with n equals 3, then we have found our counterexample. All right, so we've got 4 minutes. Let's see. I've got a fun question for you. This is on page 97. Number 10. In a popular word game, one is given a starting word and then must change one letter at a time, forming a valid word at each step, and you end with another given word. So if you're given dog and cat, you can change, and you want to change one into the other. You could change the D to a C, so dog into cog, the G to a T, cog into cat, cot, and then the O to an A, cot into cat. And so can you find a sequence of words to move from shirt to pants? So that's the first step. And then prove that you have to have at least 2 vowels in that sequence. Say that again? At least, so yeah, so at least one of the words of the sequence must contain 2 vowels. So neither of these has 2 vowels to begin with. But somewhere in the sequence, there is a word that has 2 vowels. So first, find a sequence. So yeah, talk with your neighbors. Yeah.
Is it asked for any sequence from shirt to pants or any sequence between 2 words?
From shirt to pants.
Like a word in a class.
a little bit.
Like you're staring at your connections.
You shoot.
That's two vowels, but doesn't like you.
That's two letters, though.
I know, I'm saying that's what words that has two vowels. Yeah. Two.
Like, sure, we're just say fine, okay. I can do it, but shoot.
I mean, cog is a word and that like it may take a few sequences to get there.
But it's not.
Shirk?
Technically, it's.
Yeah, I thought shirk was a word.
See the answer. It's Christian.
All right, we can talk about this next time. Thank you. I will have your exams for you next time. I will also have your homework 3s. Fingers crossed. I apologize it's taken me so long. Homework 4 should have been due at the start of class. So yeah,
Plans. That's yesterday. I just locked it and finished it.
that's fine. Yeah, thanks. See you Monday.